Maybe. There we go. Okay. So 3.5 is all about modeling with exponential and logarithmic functions. So if you remember back to when, I think it was sometime in chapter 2, we talked about putting data in tables and then using the parabola or the cubic or the quartic of best fit. And finding those best fit functions. We're gonna do the same kind of thing here, except with exponential and logarithmic functions. So we're gonna talk about how we would type that in, what it would look like to use Desmos to help us find the exponential or logarithm of best fit. So here we go. Before we can talk about or do an example, really, we need to talk about what the different, not that, there we go, what those different models are going to look like when we type them in. So here we go, 3.5 modeling, and this is actually just called NonLinear Regression. So this is kind of the second part of modeling with nonlinear regression, because the ones that we had talked about in a previous chapter involved nonlinear regression because they were quadratics and cubics and things like that. We're just kind of adding on to our options here. So the first one that we're going to talk about adding on to our options is exponential functions. So exponential function, if I'm going to find my exponential of best fit, if we made our tables in Desmos, the first step always is to make a table, and one of your table columns is x1 and the other is y1. So your exponential that you would type in to figure out what it is, y1, that little squiggly, a times b to the x1 power. So then what it'll give you is it'll spit out a value for a and for b. So then your function, f of x, is going to equal a times b to the x. So this is what you would type on one of the lines, and then whatever it tells you that a and b are equal to is what you would plug into this to figure out what your function is going to look like. So that's for an exponential. The next one we'll do is for a logarithm. Hinderpup, come on. My dog gets so worked up. All right, logarithm. Okay, so for a logarithm, it's going to look very similar. We still have starting with the y1, but then it's going to be equal to a times the natural log of x1 plus b. So then this will spit out a value for a and for b. And so then you would plug it in to f of x equals a natural log of x plus b to get what your function is actually going to be. Okay. There's a couple other, I guess, models that you would also see. These are going to be the two main ones that we deal with today. But there is something called a power function, although it's not as often referred to, especially in today's lesson. y1, and then it's a times x1 to the b power. So then your function would look like f of x equals ax to the b. And then there's also quadratics that we already know. So this is just kind of adding on to our list. That was that ax1 squared plus bx1 plus c. And then your function was ax squared plus bx plus c. And then there's also one more called logistic growth that we'll briefly mention today, because it's kind of it goes along with the exponential function. Pups, come on, man. Ridiculous. Okay, so for logistic growth, it looks a little bit different. You have c over 1 plus a e to the negative rx1. Okay, and this is one that when we talk about population, a lot of times logistic growth comes into play. Pup ran away. Sorry. Otherwise, we could see the pup. So the logistic growth has to do with exponentials when we talk about population, especially if you've had like biology and talked about carrying capacity before. You'd know that some environment can't handle the continuous exponential growth of a population, right? After a while, because of competition for resources and things like that, the population kind of reaches this carrying capacity that it can no longer grow the population beyond that. So that's where the logistic growth model comes in. And we won't talk about this one too much more today. It's just an interesting thing to think about. So C is your carrying capacity. Which is that number at which point the population can no longer grow beyond that point because whatever ecosystem or environment it's in can no longer support further growth. So that's logistic growth. If you end up taking Calculus BC, actually we do dive quite a bit more deeply into logistic growth, and it ends up being a really fun, interesting unit. It's one of my favorites. So if you have enough years left in high school to take Calculus BC eventually, I recommend it. But anyway, the ones we're going to focus on today are the exponential and logarithmic growth. And so some things we need to keep in mind when we're looking at our scatter plots, because the first thing you do whenever you start working with any of this is make your scatter plot using the table function. When you're making your scatter plot, if it looks like it's growing faster and faster and faster, that's likely exponential growth, because remember, exponentials looked a lot more like that. If it's logarithmic, it's going to look like it's growing faster at first and then kind of leveling off. So that's going to look a little bit more like a logarithm there. So keep those things in mind as you make your scatter plots. You can try both to figure out which one is going to be the best fit, but at the end of the day, the exponential or the logarithm being the best fit can pretty easily be determined by what the scatter plot looks like. So here we go. We're going to try this out with some actual data. So I'm going to write down a data set here actually real quick, and we will plug it into Desmos and give it a go. So this data is, let's see. We're going to have the year, and we're going to have the tree frog population. And this is a rare type of tree frog that almost went extinct. So in the year 2001, there were only 16 of them left, but then they made a miraculous recovery. And in the year 2002, there were 35 of them. In 2003, there were 70. In 2004, there were 135. And then there were 278. And then there were 546. Okay. So we're going to plug this data in and see what we get. So there's our data set. And let me see if I can actually split this screen. Okay. So remember, in order to put our data into a table, first thing you need to do is click the plus and click on table. From there, we need to put in our data. So the X's are going to be the years, the Y's are going to be the population. And after a while, it kind of notices what you're doing, usually on the X's, so you can kind of just, it'll autofill for you a little bit, which is kind of nice, especially if your X's are just going up by a consistent value. And then the tree frog population. Oops, I skipped a row. Okay. So there we go, but we can't see any of the data because we aren't looking in the correct range. So in order to see it, you want to click the wrench. And then you want to, on your x-axis, choose something that seems reasonable for your x value. So I'm going to go the year 2000 to 2010. And then on my y values, we're going to go from 0 to 700. And then usually it chooses reasonable steps on its own. But if you want to, you can put in that you would like it to increase by every 2 years or every 3 years on the x-axis. And then every, 100 or 50 or whatever you would like to increase by on the y-axis. And then we can see our data. And we notice that this looks pretty exponential. So that's a good sign that we should be using an exponential function to model our data. So then we want to click the next line below it. And referring to our list and referring to the one that you can't see, the exponential, this is what we're going to type in, y1 ab to the x1. Some parameters may be too large or too small to represent accurately. All right, well, this is not great data that I made up then. Whoops. What if we went, sorry guys, one sec. That's a lot better. Okay, so instead of doing just the straight up year, we're gonna do just years after 2000. And that's a lot better. Okay, so yeah, this will be in the year after 2000. These are the numbers that we get. So for our x values here, we're actually going to use 1, 2, 3, 4, 5, and 6, and just know that each year stands for, or each value stands for how many years it is past the year 2000. Okay, that works better. Okay, so then it gives us an A value and a B value. So then if you want to use this to predict future values, you could type in f of x equals a times b to the x. And if I wanted to know, let's say, how many tree frogs there will be in the year 2020, then I would get f of 20. And that would tell me that there will be 8,329,238 tree frogs if the tree frog population growth went unchecked, if there were no predators, or there wasn't like a logistic growth sort of thing happening where they were competing for space and everything like that. You could also write it in if you wanted to. Instead, you could have, instead of just typing AB to the X, you could type in, or if you were asked for it on a test or something like that in the future, not that we're having any more tests for this class, but you could say f of x equals 8.81533 times 1.98961 to the x power. So you could write that out instead, and that would do the same thing. So if you were asked for it on like an actual paper piece of homework or something, this is what you would want to write out. If you're just using it to predict future values, feel free to use just the AB to the X in Desmos itself. But that's pretty much as complicated as this gets. So since we already have experience with doing this with quadratics and things like that, that works a lot better. Or it's hopefully a lot quicker to pick up. And are there any questions at this point? Or anything we want to see again? Okay. So today's assignment is going to be in Desmos. It's going to be a lot shorter than most of our Desmos assignments have been, or the only other one that we had, which was pretty darn long. This one's going to be considerably shorter, and it's going to take you through doing something like this with an exponential, and then also doing something like this with a logarithmic equation. Okay. So we're going to go ahead and leave that and go over to the assignment itself. Goodness, computer. All right. So here we go. That's modeling with exponential and logarithmic functions. Go ahead and click on that, and it should take you to this. So you would put your name in. And the first screen talks about unicorn population in a given year. So you're just going to go through, there's 12 screens. On the next screen, it'll ask you to make the scatter plot. Then it'll ask you to figure out if it's exponential or logarithmic, make a prediction, that sort of thing. And then you'll end up going through the process of typing the exponential regression model, finding the best fit for the data, that sort of thing. Okay, so at this point, you are free to go and work on this. If you have questions, please stick around and ask. And then if I have you third quarter, I will see you then. If not, it's been wonderful having you in class. Let's see.